All right. Actually, before we get started with material, I just have a quick announcement. If we go into Learn, I've actually added some new calendars. So I don't know how many of you actually use the Learn calendar, but now there's some new stuff that I highly recommend that you guys look at. So my page will look a little bit different from yours, but right now, well, on this calendar, it used to just be our 2 study groups a week, which, I mean, I send the links to Slack every study group, so makes sense that you don't use this. However, now we've actually integrated um, other calendars. The most important one being remote community events calendar. So this is in an effort to, have like more things going on other than, material. So for example, you'll see here that um, I think this is actually events from different campuses. So Chicago apparently puts out a new algorithm on Slack every week. Here you can see that career services once in a while will have webinars. So for example, this Wednesday, there is a career services webinar preparing for whiteboarding. Whiteboarding is a more software engineering thing. So all of these events will now be available to us online students, which previously wasn't the case. So this is awesome. Yeah.
Will all the cohorts will be visible?
Yeah,
here?
that's right. Well, what do you mean by, well,
So there
all
are different
cohorts will see this.
Yeah.
All cohorts will see this calendar.
Yeah. Okay. So like if I want to attend some other cohorts, which was last year, and then but like it's like this week some event is happening.
Oh, I see. Okay, so yeah, so these are events that will be open to all cohorts. There will be sometimes like cohort specific events like cohorts graduations and things like that. That's kind of up to the cohort and up to their instructor whether they want to share it and put it on here.
Okay.
Things to look out for. Next Monday at 2 p.m. Eastern, another cohort lead instructor, Raphael, will actually be walking through how to use the Spotify API. Really cool. I love the Spotify API. As you guys saw, I used it last week to make a fun little app. Another fun thing, 2 weeks from now, on October the 6th in the evening, there's actually a data science alumni panel, which I think would be really, really, I mean, I think there are three former Flatiron students who now work at these awesome places. Actually, both Patrina and Samira were my classmates, and they're both at, Patrina's at Etsy, Samira's at Bloomberg, both awesome, awesome people to hear from. And you can ask them questions of like their experience, what was it like going from boot camp to like the job search process to like, working in a new field. So I think that would be a really, really great opportunity. I mean, you guys are still pretty early on the process, but never too early to get started thinking about next steps. So this calendar will be here on your homepage. It's a weekly view, but you can like take a look at you can toggle the view options to see all the different things that are coming up. Any questions regarding this? Yeah, I think this is a really awesome thing that we've implemented here. Yeah, just a bunch of cool events that you'll see. There's industry panel, Black Excellence in Tech. This is awesome. Let's see what else is there here. Yeah, every Thursday there's a career coach AMA. If you ever had a question for career services, that's something you can do. Let's see. And yeah, all like the holidays will be on this calendar as well. And of course, like as you know, the study group links are there. But I mean, I'm sure most of you get the link from Slack anyways. All right, let's get started with section 16. So section 16 by itself is actually just A/B testing, and through like these labs is really just walking through three examples of doing A/B testing, and it's nothing completely new from what we've seen. The one that I'm actually going to walk through is the website A/B testing, just because it's like the first one that actually brings in a data frame. So I'll just like talk through the different processes. So for this this study group, I'll talk about power analysis because we didn't go very in depth last time. And then after power analysis, we will talk about A/B testing. Questions before we get started? Awesome.
So now, when is the time when A/B testing is actually used?
Right. It really depends on, well, in a data science context, it really depends on like, what your job is, right? So I will say that not every job you need to do A/B testing. The ones that I've seen that are most common are in the marketing industry, when you like put out one campaign and you have maybe different versions of the campaign and you want to A/B test to see which one is more effective. This example that we're going to go through later is, I believe it's like an Audacity website, and basically I think they like made a change to the website and only let like half their page viewers see that change, and they want to see if that change led to more people engaging with their content. And then so you can figure out whether there's a statistically significant increase in the number of impressions that a campaign makes, or like a change on your website makes. And that's the context in which we use A/B testing. Yeah. If you walk through, I think it's like website, there's a website example. This one, let me see what the example is. I want to say, I'm not even too sure what this example is. Oh, so it's like, it's just responses. It's looking at the difference between, I want to say, yeah, just different survey responses, and you can do A/B testing that way as well. It's really just like comparing a group with another group. And then I think this one is also walking through like setting up your experiment. And so these are all good ones to follow through. I will say not every data scientist ends up doing A/B testing. It kind of depends if you think this is something that you're interested in. I mean, good to know. I mean, there are not too many labs here. I don't think it'll take too much time. But I will say not every data scientist ends up doing A/B testing. It is useful as an EDA tool for sure. But for the most part, you either do a bunch of modeling or a bunch of, well, if you're not doing A/B testing, you're probably doing a lot of modeling, which is the stuff that we'll talk about next week. So cool. Any other questions? Awesome. So let's dive back into power analysis. And the way that, and power analysis, there are basically 4 elements at play. There's like sample size, effect size, alpha, which is your significance level, and power. And each of these are all like in balance with each other. I had this up last week, I think, when we talked about this, where basically you can adjust any 3 out of the 4 of these parts, and it would solve for the 4th. So for example, here we're solving for power, and for different significance levels and different sample sizes, you can see here that the power changes. The power is affected by each of these things. It also works the other way around. I could solve for alpha, solve for n, or solve for d. But the main point that we want to see here now is how we solve for power. And power of a test, if we remember correctly, the power of a test is the probability of finding an effect that is there. So is the probability of rejecting the null hypothesis correctly. Just remember, let's like really like drive that definition there.
Yes, one quick question. The website that you showed me.
Yeah.
So in that website, like if you put if we feed any data, will this be giving us the results?
Yeah, absolutely. So usually we have our significance level at 0.5. If like if you have your sample size, I don't know, like guessing at 20, and you have your effect size, your power will be this value. And of course you would decide 1-tailed or 2-tailed. But I mean, we won't use this tool to calculate power. I'll walk through like an actual like Python one-liner that you can use to calculate the power of the test.
Okay.
So this is the scenario that we have. A researcher wants to study how daily protein supplementation in the elderly will affect baseline liver fat. And the study budget will only allow the enrollment of 24 patients. half will be a placebo and half will get the supplement, and the trial will be carried out over 1 month. And they want to see if there's a mean change. They want to see if there's a significant difference in the percent of liver fat from the placebo group and the experiment group. Does that setup make sense to everybody? All right, so as usual, we have our hypotheses being set up. mu1 equals to mu2 is our null hypothesis. Basically, that there is no difference between the two groups. That means between the group that got the placebo and the group that got the supplement, no change in their liver fat. And sorry, there's actually a typo here. It's not H0, it is HA. The alternate hypothesis is that they are unequal. And just because that's the standard, alpha 0.5. Questions? All right, so the researcher needs to know what the power of this test will be to identify a change in the mean percent liver fat of 0.17. And this is just based on past results. We're going to use a standard deviation of 0.21 for each group in the power analysis. So as I mentioned with this example here, we're trying to solve for power, and we're constrained by these three other factors. So we're constrained by significance level, 0.05. Let's go back here. We're constrained by significance level, 0.05. We're constrained by the sample size, n, which is 12. And our effect size. And so this 0.17 is our effect size. Not exactly the effect size, this is the difference, and then we're gonna divide it by our standard deviation to get our effect size. Because if we remember Cohen's, let's see if we can find this here. Cohen's D, the formula for that is, let's see if they have this here. It is just the difference divided by the pooled standard deviation. And because in this case, the standard deviations are the same, it is just the same amount. All right, so to set this up really quickly, we have our sample size being 12. This is our control group that has a mean of 0, standard deviation of 0.21. Experimental mean is going to be 0.17, and our standard deviation, as we mentioned, 0.21. So what this experimental mean means, as you can see here, in all of these, like when we talk about a type 1, type 2 error, there's always this second curve here. And we never really know where this is centered, right? I feel like it's not very clear like where this is centered. So usually this is something that you want to define at the start of the test. You know, you want to define like some alternate hypothesis of where, you know, this difference is. So the difference is, I guess, part of your hypothesis in that sense. And so this second mean is why we get our experimental mean to be 0.17. Does that make sense? So what we're going to do here in this power analysis is we're going to run a 2-sample t-test over and over again. And we're going to take a look at the proportion of simulations where the null hypothesis is rejected. And that's going to be the power of this test. The power of this test is the proportion of simulations where the null hypothesis is rejected.
But then if we are going to write that, is that the target that, okay, we need to reject the null hypothesis?
So here, it's kind of hard to conceptualize because here we're not really testing a specific thing. Here we're looking at, you know, what are the parameters of this test? And so by looking at the parameter of this test, we're just going to run this over and over again. Sorry, I think I like lost the point of your question. Can you repeat your question again?
No, so yeah. Now, are we targeting towards, right, getting the null hypothesis to reject?
Kind of, yes. We want to target getting our null hypothesis rejected correctly. Because remember I said that there is still a chance that you might reject your null hypothesis where it could be like by coincidence. So there's kind of that trade-off. But hopefully as we run through this, it'll make sense, but we'll see. So anyways, this is just setting up, so this is actually the code that is in your Power Lab. I just added a few more comments, hopefully for clarity.
Yes, quick question.
Yeah.
So just to be clear, at least for me, so is this saying, or what are, in terms of what we're doing, are we, can you go up, scroll up a little bit, please? Essentially, for the experimental mean of 0.17, is this basically saying let's set that number before we do any analysis, and then
Exactly.
we want to how can I say this? Like, how would you finish that sentence? We want to see if that experimental mean is true. Is that what we want to do here?
It's not whether we want to see if that experimental mean is true. It's we're gonna say that this is the difference that we're looking for. And if that is the difference that we're looking for, what is the power of our test then? So it kind of brings us back to, like, there are these 4 elements at play. There's power, there's alpha, there's, and then there's D. So then, that difference is in D.
Gotcha. So then just to make, so basically what I'm just trying to figure, okay, so let's say, a doctor or a researcher comes and they say, hey, well, we want to find out the power based upon this particular mean or something. So is it saying that they want to find out what the data might look like before they start doing any type of studying?
That's actually more along the lines of where we're getting at, is before even like, we're not evaluating results, we're actually evaluating the test. We want to see how, that's actually a really good
that's
way
what I
of
wanted to know. Okay, cool.
Awesome. Yeah, you're welcome. That's a good clarifying question. Help me clarify.
I have another question I need to so we're looking to find the proportion of simulations where the null hypothesis is rejected.
That's right.
So what is that? Why do we want to find that? That's, again, finding if the test is valid?
Yeah, exactly. We want to see, like, the null hypothesis being rejected is basically like seeing a change. So along those lines, it's kind of, what was the phrase that you used in your question?
Is it that, or like, what is it, to make sure it's a good test, or like
Yeah, exactly. Yeah, we want to see how good the test is. And so a good test, and we'll actually see this in the second part of this power analysis, that there are different things that you can do to make your test better. And it's actually kind of intuitive when we look at each of those 4 factors that affect power. But this is just taking a look at power when you have 3 out of 4, the other 3 factors of this test held constant. And these are our constraints, because we are constrained by this sample size, this effect size, and this alpha.
And this might be something that someone would do if they were constrained by resources.
Yeah, exactly. Yeah, because in this case, you see that this study, they were restricted by, you can only have 24 patients.
Right.
And so they want to see, well, with all of these held constant, what would the power be? But later on, we'll see, like, all right, let's say we can afford to bring in more patients. How many patients would we need to get like a good power level?
Gotcha. Okay, sounds good.
Yeah, awesome. These are all really good questions. Great. So anyways, this is just setting up all of the, constants. Our n is 12, sorry. These are our control and experimental group mean and standard deviations, and the number of simulations. Of course, the more simulations we do, the more accurate this power calculation will be, but we don't want this to take forever, so we'll just start with 1,000. This code looks like a lot, but basically what we're doing here is we're starting with an empty array that is the length of 1,000, basically 1 element per experiment. And then we're gonna loop through from 0 to 1,000, and we're just gonna conduct the same t-test over and over again. However, we're not doing the same t-test for the same sample. We're taking random samples each time. So we're taking a random sample of 12 from a distribution that has a mean of 0 and a standard deviation of 0.21 to create the control group. And we're doing the same thing, but with a mean of 0.17 and a standard deviation of 0.21 for our experimental group. Does that make sense? So these are not our actual control and experimental values. These are not like these are not the actual people that went through the experiment. These are just, you know, sampling, I guess just like creating random samples of what it could look like, if that makes more sense. So here we're just running simulations of this test to see what the power would be. And basically what we're doing here, we're running the t-test and we're taking the p-value. It just looks like this because when you do this t-test, they actually give you both the t-statistic and the p-value. So that's why we're taking the first element. And then we're just basically at the end of this, p will just be a 1,000 length array of p-values. And then here, we're just looking for how many of those p-values are less than 0.05. So how many times out of 1,000 did we actually reject the null hypothesis? Questions on that? So basically, looking at this, we only rejected our null hypothesis under half of the time. So under half of the time, we reject our null hypothesis. The power of this test is 0.495, which is not super great.
Yeah, I mean, I thought this is pretty bad.
Yeah, it's not great. It's not great. Yeah, but does anyone have questions on this part before we move on to like how we can make this a little better?
So you're sort of saying the 0.9495 is not a good, so you're trying to find if it's a good test or not. So
Yeah, exactly.
What's the threshold to figure out if it's a good test or not? Or what would be how would you know?
Yeah, so it really depends on what kind of tests. The ones that, so based on our, I guess on experiments being done, if we're looking at behavioral research, 0.8 is accepted as a sufficient level of power. And that's usually what I would use to go to as a go-to threshold. But yeah, 0.8 I think is a good amount of power.
Well, so
of
because
course,
it's below 0.8, that means that it's what does that mean?
it's not a powerful test.
I see. So it's above
Yeah.
0.8. Between 0.8 and 1 would be a good test.
Mm-hmm. Yeah, so basically that's saying that if we were to use this test, the probability of finding an effect that is there is only 0.49. So that means the probability of correctly rejecting your null hypothesis is 0.49.
Okay.
Yeah, sometimes bringing it back to the probability definitions helps, sometimes it doesn't, but basically the point here is that there are these 4 things at play, and like the adjusting either one will affect the others.
So basically you want the data to show that that there will be an effect when you do the test.
Yeah, that's right.
And so when you say achieving power by increasing sample size, I just feel, I mean, maybe there are other methods to go by, to use, and when you want to increase the power, right? But it's just a comment. I don't know if you wanted to comment on it, but I just feel like if you to say achieve power, it just sounds like you want to just do certain things to make your test valid. And I just wonder if it's a point of contention in the data world, where it's like, oh, well, this is not enough power. Well, how can I get more power?
Yeah, I'm really glad that you brought that up. There's this whole field of like ethical statistics, and actually something that's very, very common that is kind of related to this is, I don't know if anyone has heard of the term p-hacking, which is basically like hacking for a good p-value. And there's like a lot out there about like, ways that you can seemingly make your test better just by like adjusting several things. And like sample size
I was actually thinking of that only, because that's what it was leading to. I thought that it's leading to p-hacking, but then I was, I did not want to jump into it because I wanted to see what exactly it's happening.
Yeah. I mean, those are like definitely valid things to be thinking about. We unfortunately don't really cover much of like, the implications of doing this in data science.
But p-hacking is not encouraged at all, right?
No, definitely not. We do not want to p-hack our data for sure. Yeah. But yeah, there's a lot of reading out there. I think if any of you are like readers of Medium, there are a lot of good articles talking about things like p-hacking and also like, you know, making your test seem better by just adjusting several of these parameters. But yeah, definitely that's like a good thing to be aware of.
See, the thing is like, it was like, okay, give me right so much of data, and right, if the more actually like when you keep on increasing the data, the ultimately the null value is not going to remain the same all the time, right? Not the null hypothesis.
Yeah, yeah. So it's basically like you're changing. So p-hacking is basically changing different parts of your tests to achieve a lower p-value. And one of the things that you can do is basically just increase your, I believe you just increase your sample size. That's one of the things that you can do to reduce your p-value. So yeah, in a very similar way, this is kind of, in one sense, you can think of it as like, yeah, you don't want to like, you know, change parameters of your test to make it seem better. But on the other hand, like this will also it might make your test better if you're able to get a greater sample size. Because if you think about it, if you're just comparing like 12 people versus 12 people, that probably wouldn't make a very telling experiment. But if you could test more people, give more people like a placebo versus an actual treatment, imagine like just the idea of having more people just makes more sense when you're testing for the effect of a drug. But a lot of tangents that we can go off on this. Point is, what I wanted to get at is there's a one-liner that we can use to solve for power. Here we can see that in stats models, which is, if anyone remembers, stats models is the same library that we use for ANOVA, and it's going to be a library that we will be using a lot of next week, starting next week. Stats models has a power module that has this t-test independent power. And so how it works is you have to first instantiate it. So whenever you see something that looks like this, where you have like variable equals to like method, it's called instantiating something. And we'll get to more of this end of mod 2, beginning of mod 3. But once you have that, you can solve for your power. So here, basically, we're giving it the effect size, which, as I mentioned earlier, would be the difference divided by your standard deviation, your alpha, and your power. And whichever, so there's 4 parts, right? There's effect size, alpha, power, and sample size. Whichever one you don't give it, it'll automatically solve for the 4th one. So here in this case, we didn't give it the sample size. So let's just say we want, you know, everything else held constant. What would the ideal sample size be? If we run this, you can see that it gives you a decimal, but you would round up. That you would have a sample of 24.95 or a sample of 25. So once you have a sample of 25 versus a sample of 12, your power goes up to 0.8. That makes sense?
So then I'm just wondering, so if you run this and it says that the ideal sample size is 25, and then you actually run the test with the sample of 25 and you find that there's no significance, then you would say, okay, that test is well, pretty much it increases the chance that test and is showing no significance is actually pretty valid.
Yeah, that's right.
Okay, gotcha. Okay, cool.
Yeah, it actually, because power is also 1 minus your type 2 error. So if your power is up, your type 2 error goes down. And so you always want to, you know, reduce both your type 1 and type 2 error. So yeah, it's a, yeah. So yeah, on the opposite
One
side.
quick question, Yash.
Mm-hmm.
That 24 is additional 24, or it includes the 12 which we have already?
Includes.
It includes. So that means like the 12 is increased to 25, then this will give a better power.
That's right.
This 2.8, it can be taken care of.
Yes.
Yes. Okay.
Yeah, that's right. And so this next part is just showing an iterative approach, where if we didn't have, I guess not if we didn't have this, but we want to see how the power of a test actually increases with sample size. So here, basically what's happening here, let's see, to explain this code, let's start at the bottom. Your sample size is increasing by 1 at every iteration. And basically what's happening here, we're doing something very similar to what we did before. Sample new random data, but with these different sample sizes. And then we're just gonna extract, do a t-test and extract the p-value. I think when I run this, it'll make a little bit more sense. Basically, this is what's happening at every iteration. It's calculating the power at every sample size, starting from 12. So we started at 12, our power was 0.47, and as you increase the number of samples, your power goes up. And as you can see here, 24 to 25 is when it crosses our threshold of 0.8. So that's why we prefer a sample size of 25. Cool. But for the most part,
can we start this from, let's say, 5 instead of 12?
Definitely, yeah. Yeah, you can definitely start that. You can start that sample size at like 1, and then just make your way up, because this will basically keep running until your power is greater than your target power, because target here is 0.8. And yeah, it'll keep running as long as null rejected, and null rejected is the power. Yeah, until your power crosses that threshold, it'll keep running. All right, and here's just plotted on a graph. We started at 12 to 25, our power just went up.
And you could do that whole test of the number of samples, 25, calculated power, with just the library that you mentioned. You don't have to write that whole code.
Yeah, you don't have to do this at all. If you already know what kind of power level you want to achieve, then yeah, definitely do this. But let's say you have like another constraint of, let's say, all right, let's say we have like a limit of like only 20 people. What's like a good, what's like, I don't know, I guess, yeah. If you have like a limit of 20 people, you wanted to see like how far away your power would be, then you could, I guess, do something like this, but you could also solve for 20. So yeah, I think this is just to show that like as the number of samples go up, your power goes up. But cool, that's a power analysis. And this is typically something that you do before you run any statistical test, especially one that is comparing two samples. I will say, if you decide to do a statistical test in your Mod 2 project, you wouldn't have to do a power analysis, because the main point of doing your statistical testing in one of our Mod 2 or Mod 3 projects is more for the sake of EDA, less so, seeing the actual effect of something. And so I guess based on why we're doing the test, I wouldn't suggest that you do a power analysis, or you don't have to. You can if you want to, but I would say you don't have to do one. Questions on that before we move on to A/B testing? All right. Now, A/B testing, as mentioned before, is just comparing two groups of things. And there are many, many different ways you can do that. One of the most common examples I see is in the marketing field. And this is actually a very good example of that. This is, as I mentioned earlier, same data set as your labs. Just to take a look at this data set, you can see that, so this is basically a website where they did something, they made a change on their website and only released that change to half of their users, or like a proportion of their users. And so basically the people who got this change are labeled experiment, and the people who didn't get that change are labeled control. And so between control and experiment, you have two possible actions. You can either just view the page, or you can click something on the page. And basically what they want is for you to click on something. So this is kind of what the data frame looks like. I think if we take a look at more, we'll see a few click examples. Yeah, you can see here that this is an experiment click, this is an experiment click, this is an experiment click. Seeing the clicks more for experiment is not a coincidence. We ideally want to see more clicks in the experiment group, but we'll take a look more in this next cell. So really, really quick EDA, running this, the number of people who viewed, 6,000, number of people who clicked, 1,800. Number of viewers who didn't click, about 4,400. And number of clickers who didn't view, which makes sense because you can't click if you don't view, is 0. So this is just like a sanity check. If you have a data set like this, easiest way to go about this, in my opinion, is just split it into 2 separate data frames. Where is that? So we just want to have our control group and our experiment group. Do that really quickly. Let's take a look at the value counts of control and experiment. So as you can see here, in our control group, we have about 3,300 views, 900 clicks. In our experiment group, 2,900 views, actually close to 3,000 views, and 928 clicks. And so actually these numbers, not as good as you guys expect, right? It's about the same number of clicks, and the experiment just has about a few hundred fewer views. So let's take a look and see if statistically there was any improvement here. All of this is just a little bit of data manipulation to make it a little bit easier. Let's look. Our sample sizes, we had, as we said, 3,300 and 2,900. I think this is the same information here, just displayed a little cleaner. And here, the average click rate in our control was 0.27, and in our experiment, 0.30. What we want to do now is just see if statistically are they significantly different from each other. Really quickly, these are the t-test formulas from old labs. There is the built-in t-test formula in SciPy, but to specifically do a Welch's t-test, you have to feed it in specific arguments, which I just didn't really feel like doing. So we have these, which are the formulas from, the functions from, I believe, the 2-sample t-test lab. And so if we just run this, and we run this t-test, we take a look that the p-value is actually 0.004. And can anyone tell me, with this p-value of 0.004, do we reject the null hypothesis or not?
You don't.
You don't reject the null hypothesis?
It's less than 0.005, right?
Yeah, actually, I'm not sure, did I even set up the hypotheses? Yeah, I totally didn't even set up the hypotheses. But yeah, that's a really good point. With no hypothesis, you can't do anything. But yeah, really good catch, you guys. The hypothesis, let's just assume the our alpha is at 0.05. Our hypothesis is that our experiment will be higher than our control. Do we reject the null hypothesis or not? Just based on instinct. What do you think, Kishore?
I think it's actually like I think Marvin is right, where we should not be rejecting, but then the value is pretty less.
Mm-hmm. Yeah.
So I mean, it's a 50-50 chance. Like at that particular time, like when you want to just reject it, you just say, okay, you go and reject it.
Yeah.
Depends on how much money is at stake.
Any other commentary on this?
So the null hypothesis is that there is no difference between the experimental page and the control page.
That's right.
Okay, so basically we're saying to reject that, we would have to have a high p-value. Correct?
Reject that, we would have to have a high p-value.
That's what I thought.
Actually no. Let me actually just like copy over some hypotheses down here, so it'll be a little bit clearer. So let's see, if we have this as our hypotheses, so we'll call this experiment, and do we call it control? Yeah, and control, and then our null hypothesis, sorry, our alternate hypothesis. We can make this, let's actually make this a two-tailed test because it won't make a difference. So E is experiment, C is control. In this case, imagine, let me pull up this p-value curve. T distribution, two-tailed. All right. Let's take a look at this one. And let's see if there are any that are. All right, let's just pretend that we have different values. But all right, in this t distribution, having a p-value of 0.004. Yeah, having a p-value of 0.004 means that the area to the outside is usually the area to the outside is 0.004. So that means that that critical t, not critical t, but the t statistic of that of the comparison between the two would likely be out here. Because if this area, this shaded area, would be either 0.05 for a one-tilt test or 0.025 for a two-tilt test, right? So if we have a t statistic that has yielded a p-value of 0.004, that t statistic would be either to the right or to the left, depending on which way we were doing the calculation, but it would be outside of these critical values.
I mean, that means like we should be, I mean, it's a no-brainer for rejecting the null hypothesis. Yeah.
Exactly. That's right. Yeah, so we're rejecting the null hypothesis. I can see why it's confusing because of like you're comparing two values and you don't know like which comparison leads to rejecting which hypothesis, which is honestly something that took me a while to get used to as well. For almost every single test that I'm aware of, every time you have a p-value that is smaller than your critical p, you reject your null hypothesis. So that's usually something I go off of. Small p-value would reject.
The confusion I felt was because it was way smaller than the actual hypothesis. It's like I'm going for 5% and this is 0.5%.
That makes a lot of sense. Yeah, that makes a lot of sense because we're comparing, we want to see a significant difference between the two groups. So yeah. You would think that, all right, you want like to see a bigger number, which that makes a lot of sense. But really, the p-value is actually kind of, again, it would depend on which way you're looking at. But in this case, the p-value is actually inversely related to your t statistic. So your t statistic in this case is actually going to be really large. Unfortunately, I don't think we have our t statistic here. But yeah, actually we might have it. Let's take a look at the t statistic here. I think it's Welch's t. There we go. So our t is actually 2.61. And if we take a look at this is 2.61 would be like outside of here. Was that confusing? Did that make sense?
Now it's making sense.
All right, yeah. Yeah. Hopefully this helped. I will say, I really do think that like statistical testing is something that like, for me at least, I got used to it with repetition and even sometimes I get tripped up still. Good news is that data scientists don't need to do that much statistical testing. But I mean, always good to know. If you can throw like some statistical testing in your EDA, it'd be awesome. But just know that it's not necessary. But cool, that is all I have for you all today. Any other questions? All right. Before we get into linear regression next week, we're actually going to take like a mild detour for Thursday's study group. Thursday's study group, we're actually going back to probability a little bit. I don't know why it's structured this way, but you'll see that we actually go back to conditional probability. So Bayes' theorem is conditional probability. So get ready for that. So that's coming on Thursday. And then finally, next Monday, we get to linear regression. I'm very excited for that. I highly recommend, I think I'll make an announcement on Thursday during study group that like after Friday, I would really recommend that we all start looking at the material for section 18, because that's going to be our very first, full data science process. For anyone who is interested in the project, the data set is actually provided. So if you want to start like looking at the data and starting to do some data cleaning, feel free. Same as last project, I will give the option to work in pairs. And so I'll post a message probably sometime next week to see interest on who wants to work in pairs. And what else? Ooh, one final thing about the project. There is, in the appendix, there's more stuff, which is not part of the curriculum currently, but there's this multiple linear regression project, which a lot of students have found very helpful because it is literally a walkthrough of what you will be doing for the end of Mod 2 project. So if you'd like to see what that process is like, feel free to look through that. Although I would say like for now, probably up to exploring your data will make sense, which is most of it. And then when we get to modeling, we'll get to modeling on Monday. So that's just a little sneak preview of the project. Any questions? Awesome. Well, in that case, answer the interview question that I put on Slack. If not, I'll never know if you guys know what the central limit theorem is. And that's a very, very important one to know. So if you have a definition, or Google a definition and please post it in a thread. And yeah, anything else?
No.
All right, then. Have a good night, everybody. I will talk to you all at your one-on-ones or on Thursday. Okay, bye.
Bye.